Right now, beneath your feet, something is moving. Not slowly, not gradually, not in the way textbooks described when you were in school. Something is moving in a direction it has never moved before, at a speed it has never moved before, and the instruments watching it have been running long enough now that the scientists reading those instruments have run out of ways to explain it as normal. The ground under every city on this planet sits above a system of systems, layered, coupled, ancient, that is behaving differently than it did 30 years ago, differently than it did 10 years ago, differently in some measurable ways than it did at any point in the 10,000 years of recorded human history. The ocean floor is cracking open along seams that were supposed to be stable. The atmosphere is thinning in layers that no living person has ever seen thin before. The magnetic field that has wrapped this planet since before the first complex life appeared. The invisible architecture that makes everything on this surface possible is weakening, shifting, and in one large region of the southern hemisphere, splitting apart in a way that was not in any model. The poles are drifting. The ice is disappearing faster than the fastest predictions. The great ocean conveyor that moves heat around the planet and keeps the climate of entire continents livable is slowing toward thresholds that the geological record associates with abrupt, dramatic reorganization. And all of it, every single one of these systems, is doing this at the same time. That is not how it is supposed to work. These are independent systems. They have different drivers, different timescales, different physics. They should not all be outside their normal ranges simultaneously. And yet here is what the data says. This is not a forecast. This is not a model output. This is not a scenario from a climate projection paper. This is what the instruments are reading. Right now, today, in real time, from satellites and seismographs and ocean floats and GPS stations anchored into bedrock on every continent on this planet. We are going to go through it, system by system, layer by layer, measurement by measurement. No speculation, no panic, no agenda. Just the data, exactly what it shows, and what it actually means for the planet that every living person calls home. Before we begin, if you find value in going this deep on what the Earth is actually doing, a quiet subscribe helps this channel reach further. Now, let's get into it. Start with the ground itself. The thing you have stood on every day of your life and never had reason to question. The continents are moving. This is not controversial. It is one of the most thoroughly confirmed findings in the history of science. The plates that carry every landmass, every ocean floor, every mountain range on this planet are sliding across the surface of the mantle beneath them, driven by convection currents in rock so hot it flows like an extraordinarily slow liquid. This process, plate tectonics, has been operating for at least 3 billion years. It built every mountain range. It opened every ocean. It is responsible for the shape of every coastline that has ever existed. What is new is not the movement. What is new is what the instruments are catching in the movement. Since the early 1990s, a global network of GPS stations, not the GPS in your phone, but research-grade instruments anchored into bedrock, accurate to within a few millimeters, has been tracking exactly where every major piece of Earth's surface is and exactly how fast it is moving. The International GNSS service coordinates data from over 500 of these stations on every continent and on islands in every ocean basin. Together they produce a continuous, real-time record of planetary surface motion that is the most precise measurement of anything geological ever assembled. And what that record has been showing, across multiple independent research groups analyzing it from different angles, is this. The velocity of several major tectonic plates has been showing anomalies, departures from the long-term average, that fall outside the range of normal variation. Not dramatically, not in a way you would feel, but measurably, consistently, and in a time window that overlaps with anomalies in other systems that this video will cover. The Australian plate is the fastest moving major plate on Earth. It moves northward at roughly 7 centimeters per year, fast enough that Australia's GPS coordinates have to be updated every few years to keep navigation systems accurate. In 2023, the country officially updated its coordinate datum for the 5th time since GPS precision made the drift measurable. 7 centimeters per year sounds small. Over a human lifetime, it is about 4 meters. Over the history of the GPS network, it is already enough to have shifted Australia's position by nearly 2.5 meters from where it was when the first precise measurements were taken. The African plate is doing something more dramatic. It is splitting. The East African Rift System is a geological feature running roughly 6,000 kilometers through Ethiopia, Kenya, Tanzania, Mozambique, and into the ocean on both sides of the continent. It is the place where the African plate is actively tearing itself apart. Along the rift, the continent is being stretched thin. The crust is thinning. Volcanoes have formed along the rift because the thinning crust allows magma from the mantle below to reach the surface more easily. The floor of the rift is dropping as the two sides pull apart, forming the long, deep lakes, Tanganyika, Malawi, Albert, Turkana, that fill the lowest points of the widening valley. The rift has been doing this for around 25 million years. That is not new. What is new is the pace. In March of 2018, a section of the rift near the town of Mai Mahiu in Kenya opened so rapidly that a highway crossing it cracked apart. Not gradually, overnight. A gash in the earth roughly 15 meters wide and several kilometers long appeared where there had been solid ground. Local residents described hearing sounds from beneath the earth in the days before. Low rumbling, the ground shaking in ways that did not match the usual pattern of small earthquakes in the region. Then the ground simply opened. Geologists who arrived to study it noted that this kind of episodic, rapid opening, rather than slow, continuous spreading, is characteristic of a rift that is accelerating. The long-term average rate of East African rift spreading is around 6 to 7 millimeters per year, but the record preserved in the rocks shows that this average is made up of long, quiet periods punctuated by rapid jumps. The 2018 opening was one of those jumps, and the GPS data from stations on either side of the rift confirmed that the spreading rate in the years immediately preceding it had been elevated above the long-term average. The East African Rift, in geological terms, is the birth of an ocean. In tens of millions of years, if the process continues at anything like its current pace, the Horn of Africa will separate from the rest of the continent. A new ocean will form between them. The Indian Ocean will eventually flood the Rift Valley. The geology of this is not speculative. The rift has already progressed far enough that geologists can identify in the rock record the same sequence of events that preceded the opening of the Atlantic Ocean roughly 180 million years ago. The Atlantic started as a rift. This is a rift. The only question is timing. But the plates moving at the surface are not the deepest part of this story. The plates are passengers. The driver is below them. The mantle, the layer between the crust and the core, makes up approximately 84% of Earth's total volume. It extends from roughly 30 kilometers below the surface to roughly 2,900 kilometers below, where the outer core begins. At those depths and pressures, rock does not behave like rock on the surface. It behaves like an extraordinarily viscous fluid. On timescales of millions of years, it flows. The same rock that would shatter if you hit it with a hammer will, given millions of years, move like cold honey. That flow, mantle convection, is what drives the plates. Hot material near the core mantle boundary rises slowly through the mantle. As it rises, it cools slightly. When it reaches the base of the lithosphere, the rigid outer layer that includes the crust and uppermost mantle. It spreads horizontally and drags the plates above it. As it cools further, it eventually becomes dense enough to sink back down toward the core. The cycle repeats over and over on timescales that make human history look like a single frame of a film. In 2022 and 2023, multiple studies using seismic tomography, a technique that uses the waves from earthquakes to image the interior of the planet, the way a CT scanner uses X-rays to image the interior of a body, identified anomalies in mantle structure beneath the Pacific and beneath Africa that were not present or not as pronounced in earlier seismic imaging datasets. A large region of anomalously hot mantle material beneath the Central Pacific was imaged at depths and in locations that were inconsistent with the existing models of Pacific mantle structure. A deep mantle upwelling beneath the African plate showed changes in its boundary structure that were not expected from models of how stable such features should be. These are not small findings. The mantle structures being discussed here are thousands of kilometers across and hundreds of kilometers deep. Changes in them affect everything above: plate velocities, volcanic activity, the heat budget of the surface. There is a feature on Earth that most people have heard of but whose scale is rarely communicated accurately: Yellowstone. The name conjures images of geysers and hot springs, of tourists watching Old Faithful. What it actually is a supervolcano. The surface expression of a mantle hotspot that has been burning through the North American plate for 17 million years, leaving a trail of ancient eruption sites across Idaho and Wyoming as the plate has moved over it. Yellowstone's last 3 major eruptions were 2.1 million years ago, 1.3 million years ago, and 640,000 years ago. The intervals are not perfectly regular, but the rough average, around 600,000 to 700,000 years, means that by the coarse statistics of its own history, Yellowstone is overdue for another major event. The USGS is careful and correct to note that the volcano shows no signs of an imminent eruption. The magma chamber is not fully molten. The deformation signals, while active, are within the range of normal variation for the system. But here is what a Yellowstone-scale eruption would mean, because understanding the scale changes the frame of everything else in this video. A full caldera eruption at Yellowstone would inject an estimated 1,000 cubic kilometers of ash and volcanic material into the atmosphere. For reference, the 1980 eruption of Mount St. Helens involved roughly 1 cubic kilometer of material. A Yellowstone caldera event would be 1,000 times larger. The ash cloud would cover most of North America. Agricultural production across the entire continent would collapse. The sulfur dioxide injected into the stratosphere would reflect enough sunlight to drop global average temperatures by several degrees for years. Small probability on a human time scale. Certainty on a geological one. The ground is moving, the mantle is stirring, and the force driving all of it, the heat escaping from the core at the center of the planet, is the same force that connects to the next system in this video. A system that is invisible, that surrounds every living thing on this planet, and that has been quietly failing in a way that most people will live their entire lives without knowing. There is a force field surrounding this planet, not in the science fiction sense, in the literal, measurable physics sense. A magnetic field generated by the movement of liquid iron in Earth's outer core extends from the planet's surface out to roughly 65,000 kilometers on the side facing the sun, and much farther on the night side, where the solar wind stretches it into a long tail. This field is the reason you are alive, not in a general metaphorical sense, in a specific physical sense. Without it, the solar wind, the continuous stream of charged particles ejected by the sun at speeds of 400 to 800 kilometers per second, would directly impact the upper atmosphere. Over geological time, that bombardment strips atmosphere away, We know this because we have watched it happen on another planet. Mars once had a magnetic field. We know this because ancient Mars rocks contain magnetically aligned minerals that could only have formed in the presence of a global magnetic field. Roughly 4 billion years ago, the Martian core cooled enough that the dynamo driving its magnetic field stopped. Without the field, the solar wind began to erode the Martian atmosphere. Over hundreds of millions of years, most of it was stripped away. Mars went from a planet with liquid water on its surface to the frozen, airless desert it is today. Atmospheric pressure on Mars is now less than 1% of Earth's at sea level. Earth's magnetic field has prevented that outcome here for at least 3.5 billion years. It is not an exaggeration to say it is the most important physical feature of this planet for the continued existence of complex life. And it is weakening. The first systematic measurements of Earth's magnetic field were made by Carl Friedrich Gauss in the 1830s. Gauss developed the mathematical framework for describing magnetic fields and organized a global network of magnetic observatories to take standardized measurements. What those measurements, and the continuous record that has extended from them to the present day, show is a field that has been losing strength since humans started measuring it. The decline over the roughly 190 years of systematic measurement is approximately 9%. 9% in under 2 centuries is, by the standards of geological time, rapid. The decline is not uniform across the planet. In the southern hemisphere, centered over the South Atlantic between South America and Africa, there is a region where the field is not just weaker than average. It is roughly 40% weaker than it should be at those latitudes. This region, the South Atlantic anomaly, has been known about since the early days of satellite operations. Satellites in low Earth orbit passing through the anomaly experience significantly elevated radiation, because the reduced field strength allows charged particles from the Van Allen belts to dip closer to the surface in that region. The International Space Station passes through the South Atlantic anomaly on approximately 10 to 15% of its orbital passes. The crew is not in immediate danger. The station has radiation shielding, but the onboard computers are more vulnerable. Single event upsets, moments when a charged particle strikes a memory bit and flips it, causing a software error, occur at higher rates during anomaly passes. NASA tracks these events carefully. They have become a routine part of ISS operations planning. What is not routine is what has happened to the anomaly over the past 2 decades. It is expanding. The area of the South Atlantic covered by the anomaly has grown significantly since systematic satellite mapping began. And in data from the European Space Agency's Swarm constellation, 3 satellites launched in 2013 specifically to map Earth's magnetic field with unprecedented precision, researchers have identified a development that was not anticipated by any model. The anomaly appears to be splitting. A second region of locally minimum field strength has been detected developing within the broader anomaly, roughly over the southwest African coast. 2 weak spots instead of 1. The pattern is consistent with what happens in the mathematical models of magnetic field behavior when the deeper source of the anomaly, believed to be a patch of reversed magnetic polarity on the core mantle boundary, is evolving in a way that projects 2 separate surface expressions instead of 1. To understand what reversed polarity on the core mantle boundary means, it helps to understand how the magnetic field is generated. Earth's magnetic field is not a simple bar magnet. It is the product of an extraordinarily complex, turbulent flow of liquid iron in the outer core. This flow is driven by heat escaping from the solid inner core below, by compositional differences as the inner core slowly solidifies and releases lighter elements into the outer core above, and by the rotation of the planet. The interaction of this conducting fluid flow with the planet's rotation generates electric currents, which generate magnetic fields, which influence the fluid flow, which generates more currents. The whole system is self-sustaining, a geodynamo, but it is never in a simple, stable configuration. The paleomagnetic record, the record of past field direction and intensity preserved in rocks as they cool shows a field that reverses its polarity completely, hundreds of times in Earth's history. North becomes south, south becomes north. The transition takes somewhere between 1,000 and 10,000 years. During a reversal, the field weakens first, then it becomes disorganized, with multiple poles appearing at different latitudes simultaneously. Then it rebuilds in the opposite direction. The last full reversal occurred approximately 780,000 years ago. The average interval between reversals over the last 5 million years is roughly 200,000 to 300,000 years. We are currently 780,000 years into an interreversal period. By the rough statistics of the recent record, that is long. Overdue. There have also been events called excursions, periods when the field weakened dramatically and became disorganized, but recovered without completing a full reversal. The most recent well-documented excursion was the La Chance excursion, approximately 42,000 years ago. During the La Chance excursion, the field dropped to roughly 6% of its current strength. 6%. The field was nearly gone. Cosmic radiation reached the surface at levels orders of magnitude higher than today. The ozone layer was significantly depleted. A 2021 study published in Science used sediment cores, ice cores, tree rings, and cave formations to reconstruct environmental conditions during the La Chance excursion. The findings were significant. Elevated cosmic radiation changed atmospheric chemistry. Evidence of increased lightning activity appeared in the geological record. The timing coincided with the extinction of the megafauna of Australia and with major changes in human populations in Europe and Asia. The study did not claim the excursion caused those extinctions directly. What it demonstrated was that a weakened magnetic field coincided with significant environmental stress across multiple systems simultaneously. Animals that navigate using the magnetic field are already being affected. Migratory birds, sea turtles, salmon, sharks, monarch butterflies all use magnetic field information as part of their navigation. Researchers tracking migratory bird populations have documented increasing navigational errors, particularly in the South Atlantic anomaly region, over the past 2 decades. The changes are subtle enough that attributing them definitively to field changes rather than other environmental factors is difficult. But the correlation is there, and the proposed mechanism is physically sound. The magnetic North Pole is also accelerating in a way that has required emergency action from the agencies that maintain navigation standards. For most of the 20th century, the magnetic North Pole drifted slowly toward northern Canada at a rate of a few kilometers per year. Around 2000, it began accelerating dramatically. By the 2000s, it was moving at roughly 55 kilometers per year, more than 10 times its earlier pace. It has since crossed the international dateline and is now moving toward Siberia. The World Magnetic Model, the standard reference used by navigation systems worldwide, including your phone's compass, had to be updated ahead of its regular 5-year schedule in 2019 because the pole was moving so fast that the existing model was accumulating errors too quickly to wait for the planned update. The field is weakening. The anomaly is growing and splitting. The poles are accelerating. The civilization built inside this field has GPS-dependent navigation, power grids sensitive to geomagnetic storms, satellite communication systems vulnerable to elevated radiation, all calibrated to a field that is not staying calibrated. But to understand why the field is changing, you have to go deeper than the outer core. You have to go to the very center of the planet, to a place no instrument has ever physically reached, where something was recently caught doing something that was not supposed to be possible. 5,100 kilometers below the surface of the Earth, there is a solid iron ball roughly the size of the Moon. Getting to it is not possible. The deepest borehole ever drilled, the Kola Superdeep borehole in Russia, a Soviet-era project that took 20 years, reached 12.2 kilometers before the heat, and pressure made further drilling impossible. 12 kilometers. The inner core is more than 400 times deeper than that. No material known to science could survive the journey. At those depths, the pressure exceeds 3.5 million times atmospheric pressure. The temperature is around 5,000 degrees Celsius, comparable to the surface of the Sun. Everything we know about the inner core comes from one source: seismic waves. When an earthquake occurs, it sends waves of energy propagating through the entire planet in every direction. Some of those waves travel as compression waves, called P waves. These waves can travel through liquids and solids. Some travel as shear waves, called S waves. These can only travel through solids. By analyzing which waves arrive at seismographs on the other side of the planet, and how long they took, and how their character changed during the journey, seismologists can construct a picture of the interior the way a doctor constructs a picture of your anatomy from a CT scan. The inner core was discovered this way, in 1936, by Danish seismologist Inger Lehmann. She noticed that P waves that should have been absent in certain shadow zones were in fact arriving, weakly but detectably. Something was reflecting them back. Her explanation: a solid inner layer within the liquid outer core. She was right. The basic picture of Earth's layered interior that is in every geology textbook today owes its existence to Lehmann's careful analysis of seismic arrival times. For decades after her discovery, the inner core was treated as a passive component of the planetary system. It was solid iron. It grew slowly as the planet cooled. It was assumed to rotate at roughly the same rate as the mantle above it, carried along by electromagnetic coupling with the outer core fluid. Then, in 1996, two seismologists, Xiaodong Song and Paul Richards at Columbia University, published a paper that changed the picture. They had been studying seismic waves from earthquakes that had traveled through the inner core along similar paths, but at different times, separated by decades. If the inner core was static, these waves should take the same amount of time to traverse the same path. They did not. Waves from more recent earthquakes were arriving slightly faster along certain paths than waves from older earthquakes along the same paths. The explanation Song and Richards proposed was differential rotation. The inner core was rotating slightly faster than the mantle above it. As it rotated, the alignment of its crystal structure shifted relative to the equatorial plane. By measuring how much the travel times had changed over decades, they estimated the inner core was rotating roughly 0.5 degree to 1 degree per year, faster than the mantle. This finding, inner core superrotation, was controversial when it was published. It was also confirmed, challenged, refined, and debated for the next 25 years. The consensus that emerged was that superrotation was real, but at the lower end of the originally proposed range, perhaps a fraction of a degree per year rather than a full degree. Then came 2023. Yi Yang and Xiaodong Song, the same Xiaodong Song from the original 1996 paper, published a new analysis in Nature Geoscience. They had assembled a dataset of seismic waves from repeating earthquakes, pairs and groups of earthquakes that had occurred in the same location, sending nearly identical waves along nearly identical paths through the inner core at different times across several decades. The inner core had, as best the data could determine, changed direction. Direction. The response from the scientific community was exactly what it should be: systematic skepticism followed by careful investigation. Multiple groups re-examined the data, the methodology, and the alternative explanations. One major alternative was inner core topography. If the boundary between the solid inner core and the liquid outer core changed shape as the core grows asymmetrically, this could produce seismic travel time changes that mimic a rotation signal. Another alternative was changes in the outer core fluid flow above the inner core boundary. Both alternatives require explanation. What changed in the outer core in 2009 to 2010, and why? Notice what both alternative explanations have in common. They do not eliminate the finding that something unusual happened around 2009 to 2010 at or near the center of this planet. They relocate it. Now consider the timing. The South Atlantic anomaly began a period of accelerated expansion and structural change around 2000 to 2010. The magnetic North Pole began its dramatic acceleration around 2000. The inner core appeared to change its rotational behavior around 2009 to 2010. Three systems that are physically coupled, all showing anomalous behavior in overlapping time windows. The coupling chain is real. Changes in inner core rotation affect the electromagnetic torques acting on the outer core fluid. Changes in outer core fluid dynamics change the pattern of magnetic field generation. Changes in the magnetic field pattern change the surface expression of the field. Where the poles are, where the anomaly is, how strong the field is at any given location. The overlap in timing across three systems that are known to be coupled is not something that can be dismissed as coincidence without explanation. The inner core is also not growing symmetrically. It is solidifying faster on the side facing Asia than on the other side. This asymmetric growth depletes the outer core fluid of iron more rapidly on that side. The compositional difference drives convection currents in the outer core that are themselves asymmetric. Asymmetric outer core convection generates an asymmetric magnetic field. The geodynamo is a chaotic system being driven by heat and composition gradients that are themselves uneven. What all of this means, in the simplest, honest terms, is this. The engine at the center of the planet that generates the magnetic field protecting all life on the surface is running in a configuration that our models did not predict, doing things that were not in the forecast and coupling those behaviors to changes in the field that are already measurable at the surface. We are watching this in real time. We did not predict it. We are trying to understand it. And the surface expressions of whatever is happening 5,000 kilometers below are still propagating upward. One of those surface expressions is the one most visible from space. From orbit, the changes happening to Earth's ice are not subtle. You can see them with your eyes. And what you see is a planet losing something it has had for millions of years, faster than anyone predicted, in ways that are already changing the shape of the planet's surface. The Greenland ice sheet contains roughly 2.85 million cubic kilometers of ice. If the Greenland ice sheet melted completely, global sea levels would rise by approximately 7 meters. 7 meters. The elevation of most of coastal Bangladesh is between 1 and 3 meters above sea level. The elevation of South Florida averages roughly 1 to 2 meters. The elevation of Amsterdam is in many places below sea level, maintained above water only by an extensive system of dikes and pumps that was designed for a sea level that is no longer stable. Greenland is not going to melt completely in the near future. The timescale for complete Greenland ice sheet loss, even under aggressive warming scenarios, is measured in centuries to millennia. But the contribution to sea level rise is already measurable and already accelerating. The GRACE mission, the Gravity Recovery and Climate Experiment, and its successor GRACE-FO, represent one of the most ingenious measurement systems ever put into orbit. Two satellites fly in formation in the same orbit, separated by approximately 220 kilometers. The system works by measuring, with extraordinary precision, the distance between the two satellites. When the leading satellite passes over a region of higher mass, a mountain range, a thick ice sheet, a dense ocean current, gravity pulls it slightly forward, increasing the gap between the satellites by a tiny amount. By tracking these tiny changes in the inter-satellite distance, changes measurable down to a few micrometers, 1/10 the width of a human hair, the GRACE system measures the gravitational field of the entire Earth continuously from space. Changes in the gravitational field reflect changes in the distribution of mass. When Greenland loses ice, the gravitational field above Greenland weakens measurably. GRACE has been weighing the Greenland ice sheet from space since 2002. What it has recorded is an ice sheet that has been losing mass at an accelerating rate for the entire duration of the mission. In the early years of the record, Greenland was losing roughly 150 billion tons of ice per year. By the mid-2010s, the average was closer to 280 billion tons per year. In exceptional years, 2019 was the most dramatic. Greenland lost over 500 billion tons in a single year. These numbers need translation. 1 billion tons of ice is a cube of ice roughly 1 kilometer on each side. Greenland is losing the equivalent of hundreds of such cubes every year. That water goes into the ocean. It raises sea levels. And because of the physics of gravity, rotation, and the shape of the ocean basins, it does not raise sea levels equally everywhere. This is the part that most discussions of sea level rise miss entirely. The ocean is not a bathtub. When Greenland loses ice, the water does not simply flow into the ocean and distribute itself evenly around the globe. The physics are more complex and more counterintuitive than that. Greenland's ice sheet is so massive that its gravitational attraction is large enough to measurably pull ocean water toward itself. The sea surface in the waters immediately around Greenland is actually elevated by the ice sheet's gravity. When Greenland loses ice, this gravitational attraction weakens. The ocean water that was being pulled toward Greenland relaxes. It flows outward, away from Greenland, toward lower latitudes. The result is that coastlines near Greenland, Iceland, northern Canada, Scandinavia, see a small decrease in local sea level as Greenland's ice melts. At the same time, coastlines on the opposite side of the planet, South Asia, the Pacific Island, nations, equatorial Africa, the eastern coast of North America south of Cape Cod, see sea level rise that is significantly higher than the global average. Mumbai sits roughly 10,000 kilometers from Greenland. The gravitational fingerprint of Greenland ice loss means Mumbai's sea level rise from Greenland melt is roughly 20 to 30% higher than the global average. The same applies to Jakarta, to Bangkok, to Dhaka, to Lagos. The cities at highest risk from Greenland ice loss are the cities farthest from Greenland, the cities least likely to be thinking about a glacier on the other side of the planet as a local problem. That is the physics. Not a policy judgment, just geometry and gravity. Antarctica adds another layer of complexity. The Antarctic ice sheet contains roughly 26.5 million cubic kilometers of ice, nearly 10 times as much as Greenland. Complete loss would raise sea levels by approximately 58 meters. The Antarctic ice sheet is divided into three main components: the East Antarctic ice sheet, the West Antarctic ice sheet, and the Antarctic Peninsula. The East Antarctic ice sheet sits mostly on bedrock above sea level and has historically been relatively stable. The West Antarctic ice sheet is a different situation entirely. The West Antarctic ice sheet sits largely on bedrock that is below sea level, in some places more than 2,500 meters below sea level. It is a marine ice sheet. The ocean can access its base, and the geometry of the bedrock beneath it creates a vulnerability that has no precedent in anything humans have had to plan for. The vulnerability is called marine ice sheet instability. As the ocean warms, it penetrates under the floating ice, shelves that extend from the West Antarctic ice sheet over the ocean's surface. These ice shelves serve as buttresses. They push back against the flow of glaciers from the interior of the ice sheet to the ocean. Remove the buttresses, and the glaciers accelerate, but the real problem is the geometry of the bedrock. Beneath much of the West Antarctic ice sheet, the bedrock deepens as you move inland. This means that as the ice retreats, as the front of the ice sheet pulls back from the ocean, the ice face that the ocean encounters gets taller. A taller ice face in contact with warm water melts faster, carves more icebergs, and retreats faster, which exposes more of the deepening bedrock to the ocean, which means an even taller ice face. which melts even faster. Once this feedback begins and the ice front retreats past the point where the bedrock begins to deepen inland, the retreat becomes self-sustaining. It does not require continued warming to continue. The two glaciers most studied in this context are Thwaites Glacier and Pine Island Glacier. Thwaites alone contains enough ice to raise global sea levels by roughly 65 centimeters. And Thwaites is the buttress for a larger region of the ice sheet that, if Thwaites were lost, would be accessible to the same destabilizing ocean forcing. Loss of Thwaites and the ice it currently stabilizes represents approximately 3 meters of potential sea level rise. In 2021, the International Thwaites Glacier Collaboration published a series of findings that were among the most alarming in recent ice science. Warm water was being found beneath the Thwaites ice shelf in locations and at depths that researchers had not expected. The rate of basal melting from the underside of the ice shelf where it contacts the ocean, was higher than previous estimates. And the grounding line, the point where the glacier base transitions from resting on bedrock to floating on the ocean, had retreated inland more rapidly than models had projected. The question that the Thwaites research community cannot yet answer is whether the glacier has already crossed the threshold into self-sustaining retreat. The data is consistent with both scenarios. The geometry of the bedrock makes it very difficult to distinguish between the two from the surface measurements currently available. Beyond the ice on the land surface, there is another form of frozen water that is changing in ways that have the potential to accelerate everything else. Permafrost, permanently frozen ground in the Arctic, subarctic, and high mountain regions, contains an estimated 1.5 trillion tons of organic carbon. Carbon that has been frozen and preserved, unable to decompose for thousands to tens of thousands of years. As permafrost thaws, that organic material begins to decompose. Microbial activity in the thawing ground processes the organic carbon and releases it as either carbon dioxide or methane. Methane is a far more potent greenhouse gas than carbon dioxide over short time scales, roughly 80 times more warming per molecule over a 20-year period. The release of even a fraction of the carbon stored in permafrost would significantly accelerate atmospheric warming, which would thaw more permafrost, which would release more carbon. Permafrost in the Arctic has been thawing at rates that alarm researchers who have been measuring it for decades. Infrastructure built on permafrost, roads, buildings, pipelines across Siberia, Alaska, and northern Canada, is already being damaged by thawing and subsidence at rates that were not anticipated in engineering projections made even 20 years ago. The ice is not just melting, it is destabilizing systems that were built on the assumption that it would stay frozen. And as it goes, it changes the weight distribution of this planet in ways that reach all the way down to the rotation axis and the core, connecting the loss of frozen water at the poles to the magnetic field, changes described earlier. Above all of this, above the moving plates, above the weakening shield, above the melting ice, there is the atmosphere. And the atmosphere is behaving strangely in a way that most people experience directly, every day, without knowing that what they are experiencing has a name, a mechanism, and a trajectory. Weather has been getting strange. Not in the vague, impressionistic way that people have always said the weather is getting stranger. In a specific, documented, physically explained way that represents a genuine change in how the atmosphere operates. The mechanism begins at roughly 10 kilometers above the surface, in the upper troposphere, where a narrow ribbon of fast-moving air circles the northern hemisphere from west to east. This is the polar jet stream. It exists because of a fundamental law of atmospheric physics. Temperature gradients drive pressure gradients, and pressure gradients drive winds. The Arctic is cold, the mid-latitudes are warm. At the boundary between these air masses, at altitude, the temperature gradient is steep enough to drive winds of 130 to 220 kilometers per hour through a corridor only a few hundred kilometers wide. The jet stream is not a smooth, circular river. It meanders. It develops waves, called Rossby waves, that undulate north and south as the jet travels around the hemisphere. Under normal conditions, these Rossby waves travel east relatively quickly, and the jet stream path completes a full circuit of the hemisphere in roughly 2 to 3 weeks. The weather patterns associated with the jet stream move with it, producing the regular progression of weather that inhabitants of mid-latitude regions have experienced for all of recorded history. Under normal conditions, the jet stream's behavior is controlled primarily by the temperature gradient between the Arctic and the mid-latitudes. A steep gradient produces a fast, tight jet stream with well-behaved Rossby waves that move efficiently. A shallow gradient produces a slower, more meandering jet stream with Rossby waves that grow larger in amplitude and move more slowly. Sometimes they stop moving entirely. This is called a blocking pattern. Arctic amplification, the documented phenomenon by which the Arctic warms at approximately 4 times the global average rate, is compressing the temperature gradient that drives the jet stream. The Arctic is warming from the bottom of the gradient. The gradient is getting shallower, and a shallower gradient means a weaker, more meandering jet stream with larger Rossby waves that are more prone to blocking. Blocking. The connection between Arctic warming and jet stream behavior was proposed theoretically by Jennifer Francis and Stephen Vavris in a 2012 paper that generated significant scientific debate and continues to be discussed and refined. The core prediction was that Arctic amplification would lead to a wavier, more meridional jet stream with more frequent blocking events, and that this would produce more persistent extreme weather patterns at mid-latitudes. The European heatwave of 2003 killed more than 70,000 people across the continent. France alone lost approximately 15,000. The cause was a blocking high-pressure system that parked hot air over Western Europe for 2 weeks during August. Normal summer heat waves in Europe last a few days to a week before the jet stream moves the weather pattern along. In 2003, the jet stream did not move it. The heat persisted. In the summer of 2010, Russia experienced its worst heat wave in recorded history. Wildfires swept across peat bogs west of Moscow. Smoke covered the city for weeks. Temperatures in Moscow reached 38 degrees Celsius, roughly 10 degrees above the July average. Simultaneously, Pakistan experienced its worst floods in recorded history. A quarter of the country was underwater at the peak of the flooding. 20 million people were affected. The connection between these two simultaneous extreme events on opposite sides of the Eurasian continent was a single blocking Rossby wave in the jet stream. A standing wave that was directing hot, dry air toward Russia, while directing cold, moist air toward Pakistan at the same time. The winter of 2014 brought the polar vortex collapse to public attention for the first time. The polar vortex is a large area of low pressure and cold air surrounding the North Pole at high altitude in the stratosphere. Under normal conditions, a strong polar vortex keeps the coldest Arctic air confined to the polar region. When the polar vortex weakens or becomes disrupted, it can split. Fragments of Arctic air break away and plunge southward into the mid-latitudes. In January 2014, a weakened polar vortex sent a lobe of Arctic air deep into North America. Chicago recorded temperatures of -27 degrees Celsius, colder than parts of Antarctica on the same day. In 2021, the Pacific Northwest of the United States and Canada experienced what meteorologists called a heat dome. Temperatures in Portland, Oregon reached 46 degrees Celsius, roughly 5 degrees above the previous all-time record for the city. Lytton, British Columbia recorded 49.6 degrees Celsius, the highest temperature ever measured in Canada, before burning to the ground the following day in a wildfire. The cause was a blocked high-pressure ridge, an amplified Rossby wave peak in the jet stream that directed hot air from the interior of the continent over the Pacific Northwest, and kept it there for nearly a week. These events are not anecdotes. They are data points in a distribution that is shifting. The statistical analysis of extreme heat events globally shows that the probability of events that would have been essentially impossible, beyond 5 standard deviations from the historical mean, is increasing. A jet stream that is slower, wavier, and more prone to blocking delivers less predictable, more extreme weather to every city, every farm, every water supply in the northern hemisphere mid-latitudes. And the jet stream's behavior is directly connected to the next system, because the same Arctic warming that is compressing the temperature gradient above is sending meltwater from Greenland into the North Atlantic below. And what that meltwater is doing to the ocean circulation is one of the most consequential and least understood processes currently underway on this planet. Imagine a conveyor belt 100,000 kilometers long, carrying heat across every ocean basin on the planet, moving water from the surface to the deep ocean and back again over timescales of centuries to millennia. A conveyor belt that has been running, in roughly its current configuration, for approximately 12,000 years, since the end of the last ice age. And that is now slowing, for reasons that are physically clear, toward thresholds whose implications are documented in the geological record and are not reassuring. The global thermohaline circulation is driven by 2 properties of seawater: temperature and salinity. Cold water is denser than warm water. Salty water is denser than fresh water. Where water is simultaneously cold and salty, it is dense enough to sink from the surface to the deep ocean. This sinking drives the entire global circulation. The primary sinking regions are in the North Atlantic, south of Greenland and Iceland, and around Antarctica. Water sinks in these regions, flows along the deep ocean floor towards the equator, gradually warms and rises in the Indian and Pacific Oceans, and returns to the North Atlantic as a warm surface current. The entire circuit takes roughly 1,000 years. The North Atlantic component of this circulation, the Atlantic Meridional Overturning Circulation, or AMOC, is the best studied and currently the most concerning. AMOC carries an enormous quantity of heat northward along the surface of the Atlantic. This heat is the reason that Western Europe's climate is dramatically warmer than the same latitude would suggest. London, at roughly 51 degrees north, has winters comparable to Chicago, which sits at 42 degrees north, 9 degrees of latitude farther south. Paris and Montreal are at essentially the same latitude. Paris winters are mild. Montreal winters are brutal. The difference is AMOC, delivering warmth from the tropics to the eastern North Atlantic and releasing it into the atmosphere over Western Europe. MOC is slowing. The direct measurement of AMOC has only been possible since 2004, when the Rapid Monitoring Array was installed across the Atlantic at 26 degrees north latitude, a line of instruments stretching from the coast of Florida to the coast of Morocco, measuring the flow of water northward and southward at multiple depths continuously. The rapid record is now roughly 20 years long. What it shows is a circulation that is variable, with substantial changes from year to year, but with a mean that appears lower in the most recent decade than in the first decade of the record. The indirect records are less ambiguous. Multiple studies using ocean sediment cores have reconstructed AMOC strength over the past 1,000 to 1,500 years. These reconstructions agree that AMOC today is weaker than at any point in the past millennium. Some analyses conclude that AMOC may be at its weakest point in over 1,000 years. Weakest. The physical mechanism connecting ice loss to AMOC slowdown is straightforward. AMOC depends on the sinking of cold, salty water in the North Atlantic. When fresh water, which is less dense than salt water, is added to the surface of the North Atlantic, it reduces the density of the surface water, making it harder for it to sink, weakening the sinking mechanism, and therefore weakening the circulation. Greenland's meltwater goes directly into the North Atlantic. Approximately 280 billion tons per year of fresh water. The meltwater from Greenland does not spread randomly. Ocean currents direct it into exactly the regions where the sinking occurs. The geological record of abrupt AMOC changes provides the clearest picture of what a significant reorganization of the circulation means in practice. The Younger Dryas, approximately 12,800 to 11,500 years ago, is the most studied example. The end of the last ice age was interrupted, abruptly and dramatically, by a sudden return to near glacial conditions across much of the northern hemisphere. Temperatures in Greenland dropped by roughly 10 to 15 degrees Celsius within decades. The cooling persisted for 1,200 years. Then it ended, almost as abruptly as it had begun, with temperatures rising by several degrees Celsius within a few decades. The cause is generally attributed to a massive pulse of fresh water from the catastrophic drainage of glacial Lake Agassiz, a vast proglacial lake that had accumulated behind the retreating Laurentide ice sheet in North America. As the ice dam holding Lake Agassiz gave way, an enormous volume of fresh water flooded the North Atlantic, disrupted the AMOC sinking, and effectively shut down the circulation. Without AMOC delivering heat to the North Atlantic, Europe and North America plunged back into near glacial conditions within years to decades. The analogy to today's situation is imperfect. Lake Agassiz was a catastrophic pulse. Greenland's current meltwater is a sustained, gradually increasing flow. But the physical mechanism is the same, and the question that keeps AMOC researchers working late into the night is whether sustained gradual input can drive the same tipping behavior as catastrophic pulsed input. In 2021, a paper in Nature Climate Change applied a technique from dynamical systems theory, looking for statistical signatures of critical slowing down, to sea surface temperature and salinity data in the North Atlantic. Critical slowing down is a phenomenon that occurs when a system approaches a tipping point. As the system gets closer to the threshold where it would flip to a different state, it recovers more slowly from small perturbations. The study found statistical signatures consistent with critical slowing down in the Atlantic over the period from 1870 to the present. The paper was challenged immediately and vigorously. Other researchers questioned whether the statistical method was appropriate for ocean data with the level of noise present in the record. The debate has continued in subsequent papers. What is not debated is what the study was trying to detect, whether AMOC is showing the statistical precursors of a tipping point transition, because the importance of that question is enormous. A significant weakening of AMOC, not a complete shutdown, but a substantial reduction, would reorganize precipitation patterns across the entire Atlantic basin. The intertropical convergence zone would shift southward. This would reduce rainfall in the Sahel region of Africa, in the Amazon basin, in the Caribbean and Central America. It would alter the monsoon timing across South Asia. Europe would get colder. The mild winters and moderate summers that northwestern Europe currently enjoys would shift towards something colder and more variable. Each system in this video, the shifting plates, the weakening magnetic field, the changing inner core, the retreating ice, the wandering jet stream, the slowing ocean conveyor, is large, consequential, and would merit a dedicated video on its own. But the reason they share a video is not merely that they are all happening at the same time. It is that they are not independent. They talk to each other. And when you map those conversations, you begin to see something that the scientific community is only now developing the tools to fully describe. In 1972, the mathematician and meteorologist Edward Lorenz published a paper with a title that has become one of the most famous phrases in all of science. Does the flap of a butterfly's wings in Brazil set off a tornado in Texas? The answer was an illustration of a principle. In sufficiently complex, non-linear systems, small initial differences in starting conditions can, over time, produce dramatically different outcomes. Earth's coupled geophysical systems are exactly this kind of complex, non-linear system. The atmosphere, the ocean, the cryosphere, the biosphere, the solid Earth. Each is a dynamical system with its own feedbacks and non-linearities. When they are coupled to each other, the complexity multiplies. A change in one system propagates into others through pathways that are sometimes well understood and sometimes not. Consider the coupling chains that connect the systems in this video. Ice loss changes the planet's moment of inertia. This is not theoretical. It is directly measured. As ice at high latitudes melts and the meltwater distributes into lower latitude ocean basins, mass is moved from the poles toward the equator. Mass moving away from the rotation axis of a spinning object changes its angular momentum distribution. For a fixed angular momentum, a larger moment of inertia means slower rotation. This is why a figure skater extends their arms to slow their spin and pulls them in to speed it up. The planet does the same thing. The rotation change couples to the magnetic field through the core. The electromagnetic coupling between the mantle and the outer core depends partly on how fast the mantle is rotating relative to the core. Changes in this relative rotation affect the torques acting on the outer core fluid. Changes in outer core fluid dynamics affect the geodynamo. The geodynamo generates the magnetic field. The magnetic field affects everything from cosmic ray penetration to satellite operations to the navigation of migratory animals. The ocean circulation couples to the jet stream in both directions. A weakening AMOC changes the sea surface temperature pattern of the North Atlantic. This temperature pattern change alters the meridional temperature gradient in the lower troposphere, affecting the behavior of the jet stream above. The jet stream couples to precipitation, which couples to ice. Changes in the storm tracks that the jet stream directs determine where snow accumulates and where it does not. The permafrost feedback couples carbon to temperature to ice. As permafrost thaws and releases greenhouse gases, the resulting warming accelerates permafrost thaw. Thawing permafrost changes the water holding capacity of soils, affecting river flow, wetland extent, and the distribution of Arctic lakes. Some of these changes create new carbon sources through the formation of thermokarst, lakes, bodies of water that form as the ground subsides under thawing permafrost, and whose bottoms produce methane through anaerobic decomposition. All of these coupling chains raise a question that has become one of the central concerns in Earth system science. Are there configurations of the current changes that could trigger a cascading sequence of tipping points? A 2018 paper in the Proceedings of the National Academy of Sciences introduced the concept of hothouse Earth, a scenario in which multiple Earth system tipping elements cross their thresholds in sequence, driven partly by human forcing and partly by the cascading effects of earlier tipping events. The paper identified a set of tipping elements: the West Antarctic ice sheet, the Greenland ice sheet, the Amazon rainforest, the Atlantic circulation, the permafrost carbon feedback, and others, and argued that these elements are coupled in ways that mean some could tip others even in the absence of further human forcing, once enough of them have already been pushed past their individual thresholds. The cascade pathway is not inevitable. It is not even the most likely outcome under current scenarios, according to most researchers who have studied it. What it represents is a scenario that lies within the range of possible outcomes. Possible, not certain. And that carries consequences severe enough that its probability, however small, deserves serious attention. Here is what the honest assessment of the current state of knowledge looks like. Multiple major Earth systems are outside their historical ranges simultaneously. This is documented, measured, and not seriously disputed. The causes are partially understood and partially open. The connections between systems are real and documented, though their magnitude and direction in many cases remain uncertain. The combination of changes is unlike anything in the recent geological record. The monitoring infrastructure watching these systems is the best ever assembled. The models attempting to integrate across them are the most sophisticated ever built. And the uncertainty about where this leads is, paradoxically, not decreasing as the measurements get better. It is in some ways increasing, because better measurements reveal couplings and complexities that simpler models had not captured. The scientists working on these questions are not hiding things. They are grappling with genuinely hard problems at the frontier of what measurement and computation can currently resolve. Let us be precise about what this video has and has not argued. It has not argued that catastrophe is imminent. None of the systems described here is about to fail in a way that produces immediate civilizational collapse. The timescales involved range from decades to centuries to millennia to geological time. The changes underway are real and significant. They are not apocalyptic on any human lifetime timescale. What this video has argued is that multiple major systems that civilization was built to be stable are not stable. That the stability of the Holocene, the 10,000-year period of unusual geophysical calm, during which every city, every agricultural system, every piece of critical infrastructure was designed, was not a permanent feature of this planet. It was a temporary condition. And the temporary condition is changing. This planet has been through worse, far worse, complete magnetic field reversals, mass extinction events that eliminated 9 out of every 10 species alive at the time, glaciations that buried continents under kilometers of ice, and warmings that melted them entirely, supervolcano eruptions that darkened the sky for years. Earth has survived all of it. Life, in some form, has survived all of it. The geodynamo has never permanently stopped. The atmosphere has never permanently escaped. The oceans have never boiled away. Earth is resilient. On geological timescales, it is extraordinarily resilient. The issue is not planetary resilience. The issue is civilizational timescale. Civilization was not built on geological timescales. It was built in the last 10,000 years, during a period that Earth system scientists increasingly describe as anomalously stable by historical standards. The ice retreated at a manageable pace. The magnetic field held roughly steady. The poles stayed roughly where they were. The ocean circulation kept operating in roughly its current configuration. The jet stream kept the seasons where they were expected to be. All of the infrastructure of modern civilization, the power grids, the satellite constellations, the navigation systems, the financial markets, the agricultural systems calibrated to specific seasonal rainfall patterns, the coastal cities built to specific sea level tolerances, the water supply systems built around specific glacier melt and snowpack patterns was designed for that stable planet. The safety margins were sized for Holocene variability. The engineering assumptions were Holocene assumptions. That assumption is becoming less reliable every decade. Not catastrophically, not suddenly, but measurably. The magnetic pole is moving fast enough that navigation databases need emergency updates. The ice is melting fast enough that Grace is watching the numbers change year by year. The jet stream is wandering enough that heat waves that should be once-in-a-thousand-year events are happening with once-in-a-decade frequency. The ocean conveyor is slow enough that the instruments measuring it are recording a trend that, extended, reaches thresholds with geological precedent. The scientists watching all of this are not panicking. They are measuring. The IERS publishes Earth orientation parameters every few days. The Swarm constellation maps the magnetic field continuously. Grace FO weighs the ice sheets from space. The Rapid Array monitors the Atlantic circulation. The Global Seismograph Network listens to the core. The permafrost observatories in Siberia and Alaska watch the ground temperature at depth. None of these instruments has been turned off. None of the measurements has been stopped. The data is arriving. Three questions sit at the center of what Earth system science is now working hardest to answer. The first is whether the inner core's change in rotational behavior represents the beginning of a new phase in the coupled core mantle magnetic system, or a temporary fluctuation that will return to the pre-2009 pattern. The answer determines whether the magnetic field changes currently underway are accelerating toward an excursion or reversal, or whether they may stabilize as the core dynamics settle into a new configuration. The second is whether the West Antarctic ice sheet has already crossed the threshold into self-sustaining retreat. The answer determines whether the roughly 3 meters of sea level currently held in the ice behind Thwaites are committed to eventual release, regardless of future warming trajectories. It is one of the most consequential, unresolved scientific questions on Earth today. The third is whether AMOC is approaching a tipping point, or whether the slowdown measured over the past 2 decades is a trend that will continue gradually without triggering the kind of abrupt reorganization visible in the Younger Dryas record. The answer determines the future of precipitation across the Amazon, the Sahel, South Asian monsoon systems, and the thermal character of Western European winters. None of these questions has a definitive answer today. All three are being actively worked on by researchers with the best instruments and models ever brought to bear on them. All three will have more data available next year than this year, and more the year after that. Science is moving. The picture is getting clearer, even as the clarity sometimes reveals new complications. What is clear right now, today, from the data already in hand, is this: the planet is in transition. The transition is happening on a timescale that is fast by geological standards. It is happening across multiple systems simultaneously. The systems are coupled in ways that can amplify changes and pass them from one domain to another. The civilization currently living on this planet was not designed for a planet in transition. It was designed for a planet at rest. That planet, the Holocene planet, the stable, predictable, mild, well-behaved planet that allowed everything from the first agricultural civilizations to the internet to come into existence, is not gone. Its legacy is everywhere. But the physical conditions that produced it are changing. The new equilibrium the planet is moving toward will be different. How different and how fast the transition proceeds is the question the data is still working to answer. Somewhere 5,000 kilometers below you, right now, iron is moving in total darkness under impossible pressure. It has been moving for 4.5 billion years. The field it generates as it moves has surrounded this planet for longer than complex life has existed. That field is changing. The core driving it is doing something new. The ice recording the history of the atmosphere above is retreating. The ocean carrying heat around the planet is slowing. The ground carrying every city on its surface is shifting. All of it is being watched. All of it is being measured. All of it is being thought about carefully by people who have dedicated their careers to understanding it. And all of it, every measurement, every model, every revised estimate, points toward the same simple, enormous, still unanswered question. Where does this go? The instruments are running. The planet is still turning. And the answer is already written in the way it moves. We just have not finished reading it yet. If you could ask the Earth one question, just one, knowing it could answer, what would you most need to know?